Today we are going to talk about plastic injection mold design.
Yeah, it's quite a process.
We're looking at how you get from just a digital file, a CAD model, to this really heavy-duty, durable tool for manufacturing.
Right.
But the challenge, like right away, is that it's not just one kind of mold. The expectations for how long that tool needs to last, well, they vary wildly.
Yeah.
That sort of defines everything else.
That's exactly right. You're hitting on the SPI classification system. It ranges from these super high volume tools meant for millions of cycles all the way down to, quick prototype molds.
Right.
And that whole spectrum dictates the kind of expertise you need. A company like True Position Plastics, for instance, they handle that full range. They can help customers with everything from those high production class 101 molds right down to the simpler prototype ones.
And that range requires deep experience, I imagine.
Oh, definitely. The owner, Justin Church, he actually brings over 25 years of hands-on experience. He's been both a mold maker and a mold designer, which is, well, pretty essential when you're navigating all those different requirements and materials.
So these classifications, they set the stage for cost and complexity.
Yeah.
You've got class 101 built for, over 1 million cycles?
Yeah.
Using hardened tool steels.
Right. Hardened steels, precision cooling, the works.
Versus, say, a class 105, which might be aluminum, maybe only needs to survive like 500 shots just for prototyping.
Exactly. Big difference in materials, design complexity, and of course cost. But, before we even pick the steel, before any metal gets cut, we absolutely have to nail that initial product review. Is the part actually designed for manufacturing? Because if it's not,
the mold's doomed from the start, regardless of the class.
Pretty much. We're looking for things that seem basic but have huge impacts, like proper draft angles so the part pops out easily.
Right, no sticking.
Uniform wall thickness helps prevent warping, and, making sure there are proper radii fillets to avoid stress points in the plastic part later on.
Okay, so product design first. Then you move towards predicting issues. I find that mold flow analysis part really interesting. It's like crystal ball gazing for plastics.
Well, it's a bit more scientific than that. But yeah, it's highly predictive. It's crucial for saving time and money down the line.
What does it catch?
It shows us potential problems, like where air might get trapped inside the cavity, or where weld lines could form, or if the plastic might not fully fill the mold a short shot.
Okay.
And seeing that early lets us optimize things. We can figure out the best place to put the gate, where the plastic enters, and how to vent the air out properly, all before finalizing the tool design.
Makes sense. So speaking of the tool itself, let's talk materials. That seems like a major cost factor, especially for those high-volume Class 101 molds.
It really is. That's where you see key trade-offs. A common choice is number 2 steel, P20. It's a good workhorse, pre-hardened steel. But for the really high-volume stuff, millions of cycles, the sources often point towards using number 7 steel. That's a 400 series stainless.
Stainless steel, why?
Primarily for the A and B plates, the main mold halves. The big reason is simple but critical. Stainless prevents the cooling water lines from rusting over time.
So it maintains cooling efficiency and extends the tool life.
Exactly. Reduces maintenance headaches and protects that big investment for, you, the customer.
Got it. Okay, 2 more quick engineering things we have to touch on. First, the actual size of the mold cavity has to be made bigger, oversized.
That's right, deliberately oversized.
Yeah.
Because plastic shrinks when it cools, molten plastic always shrinks.
Okay.
So the cavity has to account for that specific resin's shrink rate, and that rate itself is influenced by the materials, sure, but also the part's shape and even how fast you run the process.
Wow, complex interaction. And the second thing?
Cooling. We mentioned the water lines. Mastering the heat transfer, the thermodynamics, is absolutely key.
For cycle time and part quality.
Right. Both. You want maximum heat transfer to cool the part quickly and consistently. The way we do that is by ensuring the cooling water flows fast enough to be turbulent.
Turbulent flow?
Yeah, engineers aim for a high Reynolds number. We often use things like baffles and bubblers inside the cooling channels to force that turbulence. Slow, smooth, laminar flow just doesn't pull the heat out efficiently enough.
Fascinating. Okay, so we've designed it, built it, cooled it. Now we got to get the part out. The ejection system. Feels maybe like a final step, but sounds just as critical.
It absolutely is, whether you're using ejector pins or blades or even puffs of air. Proper ejection isn't just about getting the part out cleanly, it's about preventing the part from sticking, getting deformed, or worse.
Damaging the mold itself.
Precisely. If the ejection system fails or isn't designed right, you risk damaging that very expensive tool. Protecting the mold investment is paramount.
So when you look at that whole journey, digital file to, thousands or millions of physical parts, it's really clear. Injection mold design isn't just machining metal. It's this intricate balance of mechanical engineering, material science, thermodynamics, software prediction, all focused on reliable mass production.
Absolutely. It demands total clarity on what you need that mold to do right from the very beginning.
If you need a mold designed, reach out to Justin Church at True Position Plastics. Justin and his team can help you with all things injection molding. You can reach them at www.truepositionplastics.com.